I am the world's most renowned expert on scientific papers because I have absolutely no experience writing them. I do hope that they will still be peer-reviewed no matter what form they take, because I think that peer review is still, correct me if you disagree, but I think that it's good to get feedback and sort of have some quality control, because the sort of scientific blogs doesn't strike me as having the same sort of quality assurance level as typical something that I would call a scientific paper. So I'll ignore the topic of scientific papers, and I'll go back to the history of Python, because that's the only thing I'm an expert on these days. So in 1990, I was a pretty darn experienced and prolific programmer. I worked for a small outfit named CWI in Amsterdam. It's actually a non-profit run by the Dutch government as an educational institution. And I had worked there for probably 6 or 8 years by then as a programmer on a couple of different projects. Mostly cranking out large amounts of C code. My first project at CWI was actually as a programmer on a team that was building a programming language. It's a programming language that no one has heard of, except when they dig into Python's history, because I think we had one user outside CWI and 2 inside CWI. But we spent 3 years building the language, and all that time, as I was trying to figure out how to implement various parts of the language implementation, I constantly came up with ideas to make the language better by adding something or taking something out. And the language designer, a guy named Lambert Meertens, who sort of took it upon himself to be my mentor for much of that time, every time I came up with a proposed improvement to ABC, he very patiently explained why that was a bad idea. Not a single one of my ideas made it into the language, except for the name. Basically, the language survived 3 years of implementation effort unchanged. When I started on the project, it was named B, but the B was cursive, and it was supposed to be the name of the variable. When you open the variable, the name of the language would come out. And then we had a brainstorm, and we couldn't come up with a good name, and that's how we chose ABC, which in Amsterdam sounded a better idea than once I visited the United States and looked in the phone book. Anyway, so ABC was a wonderful language. I loved it very much, but it was canceled after 3 or 4 years of implementation effort, and I moved on to a project named Amoeba, which also very few people have heard of, except if they study the history of distributed operating systems, because Amoeba was one of the first microkernels, and there's a ton of literature, including several very good PhD theses that came out of the Amoeba project. My contribution was, as a programmer, we were trying to create applications for Amoeba. And Amoeba was so different from Unix that it was easier to create our own applications than to try to port Unix utilities, even though we had the full Unix source code from Bell Labs available to us. So that was very tedious, and one day I thought to myself, oh, I really wish that we could write these applications in a different language, something more like ABC. Porting ABC also wasn't really a good option, because ABC was not extensible, and it would have an even harder time than the typical Unix application in doing anything useful on that particular platform. So, and this really sort of all comes down to a terrible lack of common sense and a very poor judgment on my side. I thought that in 3 months I could implement a programming language from scratch, And my manager wouldn't mind, because this was absolutely not what I was being paid to do, but my manager was on a sabbatical on the west coast of the US. And I had a lot of free time because my social life was kind of in the dumps. So I did actually, after 3 months, I had a working prototype. And I showed it to my colleagues, and I showed off simple things like, well, look, here's a variable, and you put a value in it, and you add something to it, and you print the value, and you can define a little function, and I have arrays and hash tables implemented. And everybody was ooh and ah, and can I use that? And so I was encouraged, and then I showed it to Lambert Meertens, and I think the second thing, he said, give me the keyboard, and the second thing he typed made Python crash. He was that kind of person. He had a very sort of good insight in what the weaknesses of a system could be. Now that crash was fixed the next morning, of course. I really have to fast forward because I want to give Fernando some time too. But within a year, Python was sufficiently popular within CWI that we decided to do an open source release, except we couldn't call it open source because that word had not been invented. That wouldn't be until 97 or so. But we did a release, we did it on Usenet, and because there was Usenet at the time, Python was much more easily distributed than ABC had been in the sort of the previous decade, because I remember traveling to the US with a 9-track mag tape in my luggage, which would be mounted at various Unix systems throughout the country, where people would then get the source code for ABC. And that was just a snapshot. There was no source control. There was no FTP sites even that you could use to send things around. So that was one of the things that sort of worked against ABC when it was trying to gain popularity. So I had done some simple releases of libraries to Usenet before, so I was familiar with the process. I was not familiar with that particular outcome because immediately my inbox was overflowing with feedback and requests for features and bug fixes and patches, and sort of immediately people said, whoa, we want more of this. So I spent, well, I guess the next 28 years or so trying to give people more of that. First by doing a lot of coding, then by sort of letting other people help with the coding, letting other people create a community. That was not really my strength. But when people said, well, we should create a news group, we should have a conference, we should do other things, I said, sure, do it. And apparently that's a good way to create a community, to sort of encourage people to scratch their own itch, not just when it comes to code. And so before I hand the mic to Fernando, sorry, it's still mine.
I'm learning a lot.
I want to talk about some of the earliest memories I have about, now not about coding, specifically about adding support for scientific data sets to Python. In the mid-90s, when I had moved to the US and we had started having regular Python conferences, I met a guy named Jim Yugunin, who was also an incredibly prolific coder. He also had the advantage of having gone to MIT. Eventually, we ended up hiring him. He created something when he called it, he called it JPython, but for various copyright reasons, it's now known as Jython. Years later, he also created something named IronPython, which was a Python implementation on top of Microsoft.NET. But in the late 90s, before he did JPython, he wrote something called Numeric, which was the predecessor of NumPy, and it had a lot of the same things that NumPy had. The implementation was just a little crankier. I think NumPy was sort of when numeric became so popular that it required a rewrite, NumPy became that rewrite. And so Jim knew a lot more about scientific data processing. So he knew that Python arrays were not very efficient because every floating point value in Python is not taking up 4 or 8 bytes, but probably 32 or so, because it's an object and it has a reference count and a type pointer and memory allocation overhead. And so if you have an array full of those, you also, in addition, have all the space needed for the pointers to those objects. So an array of 1,000 floating point numbers would not take, like 1,000 floats in C is like 4,000 bytes. In Python, it would probably be 40,000 bytes or so. So Jim had come up, fortunately, Python was very extensible. One of the things ABC was not. And so it was fairly easy to add a floating point array construct to Python. But Jim had some other plans, and he also wanted to support other popular data types, in particular complex numbers. And so he pleaded successfully to add complex numbers to Python. He also, because he was doing a lot of wild stuff with large arrays of numbers, he did a lot with slices, which is how you sort of take a part of an array. And he invented the ellipsis notation that you can use to say, well, in all the other dimensions, just do everything. I forget if he was also behind the sort of extended slices where you can give a stride, but I wouldn't be surprised if that was also a request that came out of NumPy. So then if we fast forward to, I think, around 2005 or 2006, NumPy had been created as numerics replacement, and Python 3 was in the works. And an enterprising young man named Travis Oliphant came to me at some Python conference, I believe, and he asked for a better way to pass arrays of floating point numbers between C extensions. We get into a lot of detail, but he wrote a very complex, over-engineered proposal named PEP 3118, which, because I thought, well, he's the expert on numeric arrays, I read it over. It all read like, okay, it didn't have internal inconsistency, so I accepted it. I think it took 5 years before most of that was actually implemented, but we do have support for all that now, and I think NumPy is more successful because of that. And really, I want Fernando to take over so that we'll also have some time for questions.
Thanks, Guido and Dennis. So I'll try to sort of give a similar counterpart to that. There's some interesting parallels in the early history and the patterns. I was a graduate student in physics in Colorado in 2001, flailing terribly on my PhD at the time, and having been fired by my first advisor, having been picked up by a second advisor, which is not a great career move on your 5th year. To the grad students in the room, I don't recommend it. But one thing that I had was a very complicated pipeline. My PhD was analyzing data from supercomputer simulations of particle physics. And I had a big hodgepodge of literally language books on my desk. I had the big Perl book. I had a Unix book because my advisor was an absolute wizard. She was a magician with awk and set and wrote the most complicated and most elaborate awk and set scripts. And I had an IDL book and a Mathematica book and the Kernighan and Ritchie C book. And so I realized I was probably spending far more time switching between programming languages than getting anything done. And my office mate says, you should look into this Python thing. It's kind of like Perl, but nice. And you can use it interactively, and this is going to be important. And I played with it, and I remember reading the basic Python tutorial that ships with the documentation. And and just falling in love with it. What happened was I was a reasonably competent Perl programmer at the time. I'd written some code. I'd actually picked up a little open source Stanford thing for making like web pages of pictures, of galleries of pictures, and within 24 hours of using Python, of just reading the tutorial, I knew how to do things in Python. Not just that I didn't know how to do them in Perl, but I didn't know if they were possible in Perl, right? And to me, that was the sign of a good tool. It was a sign of a clean design. I thought, if in 24 hours I can be this proficient with this tool and I can keep it in my head, there's something clean about its design and expressive about it that I really want, and I want it as my everyday tool. But what it had missing was a better interactive environment. And this comes from kind of the two cultures that we have. Guido came from a culture of software engineering, and I came from a culture of scientific programming and scientific data analysis, where for me the computer was really a tool to look at data, to look at a problem, to think about a question. So the interactive workflow was really important, and that also included things like give me quick access to the operating system, give me quick access to changing directories, to opening files, to running a script, but then typing code interactively one variable at a time. And Python has a basic shell, but it's fairly basic. Nothing wrong with it. It served its purpose. And I looked online, and there were two other projects out there. There was a blog post from the O'Reilly network about two other systems, one from a grad student at Caltech called Lazy Python, and one from an oceanographer in Germany. The student at Caltech was named Nathan Gray, and Janko Hauser was an oceanographer in Germany who had written something called IPP, the Interactive Python Prompt. And I emailed both of them, and I said, hey, you've both written tools for interactive computing in Python. I also have this thing called IPython, which was the beginning of a little souped-up shell for Python. Do you want to join forces together? And they both gave me more or less the same answer. They said, nope, too busy right now, got work to do, go for it. It's open source, do whatever you want with it. So from the very start, IPython was born as a collaboration. It wasn't my work. It was really the spirit of people putting their stuff out on the internet and being willing to share it. I told my advisor, this is going to take an afternoon. Not 28 years, but 18 years later, here we are still. So we have trust us equally on the quality of our time estimates. I also disappeared. It wasn't what I was being paid for. I came very close to not graduating. But 6 weeks later, I emerged basically from a sort of 20 hours a night, 20 hours a day coding binge where I stopped going to the department. It was kind of a mess. But out was IPython 0.1, which I announced actually on Complang Python in December of 2001. And it was a very similar process. I really was in a bad place with my PhD, but what happened was I put this thing out, and immediately people, my God, what about this? What about this idea? The mailing list at the beginning was my personal email. I literally put this out and I said, if you have any questions, email me at colorado.edu. And immediately people began providing feedback, ideas, and that was pretty exhilarating, actually, to basically realize that maybe this PhD thing isn't going so great, but there's something I can do, and there's this community of other people who want to use this tool and who want to build it. A couple of years later, I did graduate, by the way. I'm faculty at Berkeley now, so it works out in the end. But a couple of years later, I traveled to a conference where I met Travis Oliphant and Eric Jones and kind of the early crowd of the scientific Python world. This was when I was still using numeric. At that point, I was a postdoc in applied mathematics at CU Boulder, writing software for basically developing methods for partial differential equations on top of numeric, and with a lot of handwritten C++ and Fortran code that was precisely possible to integrate because Python was extensible in this manner. I went to this conference, which was an outgrowth of basically Jim Hugonin's work, and this community was now beginning to coalesce. So the first versions of that conference had maybe 80 or 100 people who got together at Caltech once a year with some support from the Hubble Space Telescope because astronomers were early adopters of Python as a tool for science. And what happened was I basically found my people, right? I found my tribe. These were other scientists. They were astronomers. They were scientists. Travis did his PhD in EE, and he had done a postdoc in medical imaging at the Mayo Clinic, I think. So people who came from different scientific disciplines, but who had this common interest in building open source tools for science together. And for all of us, Python had this interesting set of features that resonated back from that very first day with me, which was very expressive, very high level, very easy to think with. We could use it interactively, which really was critical for our workflow and the kind of questions that we were asking. And with this clean extensibility model, that meant, yes, Python, a list of Python floating point numbers would be a terrible way to represent scientific data, but we had this opening, we had this hatch that let us write C code, that gave us numeric and its evolution into NumPy, that allowed us to link in the decades worth of high performance, well-tested numerical codes in Fortran that could all be made available because you could link them through a C API. And that made it viable to have a modern ecosystem with a high-level tool that we all loved and that we were all kind of really, really excited to use, and with most of the performance bottlenecks, at least a way to tackle them. It wasn't perfect. There continues to be debate, and people continue to iterate on ways of working on the performance issues and better ways to express that. But the point was there was a way through. And that community really began to grow. There was a very interesting dynamic with what I would call kind of the core Python community, meaning Guido, the people who went to PyCon, that these were two parallel communities, but they were co-evolving in interesting ways, and there were conversations that happened across. Guido already mentioned the influence of the complex numbers, etc. The counterpart is that we learned a lot. We learned a ton at various levels. Technically, there was the fact that we as scientists didn't have to be compiler experts. We didn't have to learn how to write a programming language. We basically had this other entire community that had that as their job, and they were good at it, and they were willing to talk to us, right? It was possible. It took work. You had to write PEPs. You had to go through their governance process, but they were willing to talk to us. They were willing to listen to our needs and to implement those in the core language. And at the same time, that freed us to work on writing things like IPython or NumPy or Matplotlib for data visualization, or symbolic programming libraries like SymPy, or the entire SciPy stack, and now the vast kind of ecosystem of other tools that exist in that world. We could focus on that and sort of trust that we had this foundation that we sat atop of. That's a different dynamic that, for example, the R community has. Nothing wrong with it, but it emerged through a different historical pattern. R was developed by statisticians, and effectively the same team builds the core language, the core infrastructure, and all of its extensions. It's basically all in one world. This was a different dynamic. And I remember having slides when I started sort of evangelizing Python as a tool for research, where I made the point in 2004, 2005, 2006, when we began really pushing these ideas out in scientific conferences, of saying, look, today, the job of scientists is actually getting much more complicated, in that as a scientist, you may need to interact with a database engine. You may need to parse and process nasty, complicated plain text files with regular expressions. You may need to expose your compute engine over a web server to talk to some other remote service, et cetera, et cetera. You're going to have a ton of things to do that go beyond writing number crunching Fortran codes, right? And so you want to do that in an environment where people who know what they're doing are building all those tools. And for us, Python was that, right? Python was one of the mottos of the language is batteries included, meaning you install Python and the standard library has a bunch of that stuff out of the gate. You don't have to do anything else. There may be fancier versions of maybe almost each of the tools in the standard library. Maybe somebody has developed a more sophisticated, richer, but the core one is probably pretty good for a solid start. And that was huge, right? Because it all of a sudden meant that scientists could tackle far more complicated use cases and problems with this rich foundation that we weren't responsible for maintaining. So this is kind of the technical part of that dialogue with this community. But there was also a human side that at least for me personally was super important, which was learning how to run an open source community, right? And both the human aspects and the software aspects, but not the specific libraries, but rather the software development processes of those communities. So we were, as scientists, okay, the idea of sharing your stuff, that wasn't so weird. I mean, you publish papers, but the notion of collaborative software development online, processes for doing that effectively, things like unit testing and version control, and all of those things, we learned them from just lurking on the Python mailing lists, reading, interacting with them, we were always welcomed there. I occasionally would post on either CompLang Python or even the core Python mailing list, and a number of us scientists occasionally kind of peek our heads in there if it's relevant. And we learned a ton. We learned a ton from watching how Guido managed kind of the growth of that community, the growth of the conferences, and even as more complex social issues began emerging, issues of diversity, issues of inclusion, issues of conduct. All of those things, we always basically followed sort of what was happening in the Python community as a way of learning, because the Python community in that sense was pretty much ahead of us in many ways. On issues of reproducibility of the core scientific workflow, I remember giving a keynote at PyCon 2014, I think, in Montreal, where I was basically saying, in many ways, the open source ecosystem embodies the ideals of scientific research better than we scientists do, in terms of making their stuff tested, making your bugs publicly available, making the process for that something which is exposed to the entire community, having processes that automate a good amount of the checking and validation and that ensure that problems don't come back. Many of the things that we claim to do in the scientific world are in many ways done more cleanly by the open source software community, and that dialogue has been extremely important. I don't know today the discussions on reproducible research and the David Donahoe and John Claerbout and Buckheit quote that we all have in our talks from here from Stanford about reproducibility and whatnot that we've been kind of parroting for 20 years. That today is kind of part of the zeitgeist. You see editorials in Science and Nature and whatnot about those issues. I'm not sure how much people realize that a lot of those ideas we pulled very, very strongly from the open source community, and for many of us that meant from Python. I mean, obviously, other communities had similar flavors, but for many of us, because Python has been so important in research, we were drawing that knowledge from the Python community. So I don't want to go into kind of a full history of what came after IPython. There's plenty of talks about Jupyter online, so if you want to see either the 15-minute or the 20-minute version or the 30-minute version or the 40-minute version, I have them all. You can watch those online. So I think it would be, I thought it would be more interesting and more valuable here precisely to sort of have this conversation on how our communities have learn from each other. I hope we scientists have also contributed use cases to Python, a richness of users, of challenges, of performance constraints, of ideas. Today, for example, at UC Berkeley, I was mentioning to Rosemary, I spent last year teaching the core data science courses for our new major in data science. The upper division course I had 850 students. The lower div course, Foundations of Data Science, has 1,400 students. These courses are reaching basically more or less all of the entire Berkeley campus. All of that stuff is in Python. And so Guido in 1999 wrote a grant proposal to DARPA called Computer Programming for Everyone. That didn't get funded, right? Did it? Or?
Funded a little bit.
A little bit, okay.
And then I learned a lot about how funding really works.
Okay.
And then I ran.
So this was in 1999, and I would say that today we may have a version of that in sort of data science for everybody, not maybe focused just on programming, but also on the layer of data and analysis that at least at Berkeley we're doing it, and it would be unthinkable if it wasn't, because we have this entire open stack that starts in Python and has NumPy, everything up to the high-level tools on which we can deploy these courses, these educational materials. And so, at least for me, it's been a hugely productive kind of dialogue now of almost 20 years. I've learned a huge amount. It literally made my career possible. And I think these communities continue to learn from one another. The one thing that I do want to say about Jupyter is that I definitely wasn't the inventor of Jupyter. I may have hidden from my advisor and told her that it would be an afternoon in 2001 for IPython, but what we know as Jupyter today is the work of a huge community, and it would be unthinkable if it wasn't. Not just those other two people who gave me a seed of code for IPython in 2001, but especially people like Brian Granger and Minrigan Kelly and everybody who came after that, with whom we've built what is Jupyter today, both technically and in terms of the human community. And we do have people who straddle the two. For example, one of the directors of the PSF is an engineer called Carol Willing, who Guido knows very well. She is also part of the equivalent kind of directing body of Jupyter, a core contributor, part of our steering council. So we even have kind of human links that are deeply embedded at the core of both community, like Carol Willing.
So Fernando, it seems to me,
one of the things that really intrigues me about Jupyter is that, in a sense, this is a tool for representing. Oh, yes,
So that's recorded, I guess? Or
Yes.
your audience?
It seems to me that this is a tool which is serves several purposes. It's used by the developers as a way of expressing what they're doing and a good way to interact with complicated supporting systems, the various tools that exist in the environment of the Python system. But it's also a very good way of writing a paper. And in fact, I can see where, given the vast number of options that you want to explore when reading a complicated computer science paper or economics paper or whatever, you want to explore the data that's there, the algorithms themselves, and you want to do this dynamically. And so presenting the information to your readers through a Jupyter Notebook is in fact a better way of publishing information than writing a paper. And this is a replacement for the paper if we can get everybody to do it. And the interesting thing about it is that they're all all of the Jupyter systems are in some sense compatible, and so the papers can be executed in a variety of different environments and tested much more broadly, and students or researchers can experience the problem of discovery and explore ideas which they would not otherwise be able to do. Static papers are kind of boring. I read a lot of them. Papers that are much more dynamic are much more interesting to read. So anyhow, have people started to adopt this? Is there a journal yet that wants to submit it in Jupyter form?
So not quite to my knowledge, though there might be something out there, but as far as I know, we don't have quite any specific journal that says we can take a direct submission in this way. But the tool chains for conversion of notebooks into publishable formats are getting better and better. There's a tool called PanDoc out there, which was written, ironically, by the chair of the philosophy department at UC Berkeley. It's written in Haskell, and it's this lovely Swiss Army knife of document conversions. And thanks to the work of folks in the Jupyter community, as of version 2.6 that came out a few months ago, it recognizes notebooks. And that's important because the moment PanDoc recognizes a given format and maps it into its internal abstract representation, something like the LLVMIR for the compiler geeks in the room, then it can spit out any of its output formats. And so now with this, a one-liner, you can say pandoc -- from foo.ipynb -- to foo-docx, and you get a clean, well-formatted, with figures, with equations, Word version of a notebook. Same for LaTeX, same for HTML. So that all of a sudden begins having this. We've had conversion machinery in the past, something called NB-convert, that could convert to LaTeX and HTML. But by going through PanDoc, all of a sudden the machinery gets a lot richer and more powerful, and we've been collaborating and talking with John McFarlane about that. We also do have conversations with journals and with scientific publishers about this. There are companies that are building kind of the interactive stack and that are working with IEEE, for example. So there's a startup in New York that is working, that has connections with IEEE and is working on some of this idea of basically bundling notebooks as part of the publishing process. So I think we will get there. That's certainly our vision, and that's one of the reasons why we thought of the notebook format as something that should be, first of all, independent of the programming language itself. So even though we happen to be Python people and most of what I do is in Python, we wanted the basic idea of interactive, a document that combines natural language with interactive computation happening in a block of code. There's nothing Python specific about that idea, and you could imagine expressing it anywhere. Our protocol encodes that with the language being just a parameter of the protocol. And then the format was designed to be archival, to be very machine reading friendly, because we always imagined that not only are static papers boring, most of the literature probably needs to be read better by the machines than by humans. And so we wanted this document format to be a document format that was very machine friendly, so that it's a data structure. You shouldn't be parsing it like an animal, the way you have to do a PDF to extract metadata out of it. You should have proper metadata schemas embedded everywhere to understand what's in there, what's natural language, what's code, what's an output, what the data is, what it says. And then the machines can read most of the literature, which we don't have time to, and we're not reading it anyway because there's too much of it. And then when we do need one little bit, we can get that little bit converted to a human-friendly format with the right conversion tools.
So do we have questions, comments?
Your question?
So do we just repeat the question for the recording?
So I'm Scott from Google. I've been working on getting on notebooks as part of our commercial offerings. So love what you're doing. Keep doing it. The question, though, is you said earlier you're inspired by what Guido and team were doing in the software world, in the scientific world. There's a significant debate inside Google and among friends of where did notebooks end and where does software development begin? And are those things separate? Or what's your thoughts on those two roads coming together or not? You know what I mean in terms of, do you use notebooks for development, or is notebooks, no, I'm going to stay on the software development side? Where do those things come together?
So I'll repeat the question for the recording. What's sort of the boundary between, just give it more concisely, what's the boundary between notebooks for analysis and scripting and one-off problem exploration versus software development, software engineering, building libraries, building reusable code? It's a very, very good question. I don't think we have a full answer to it yet, because I think that answer continues to evolve. I don't think the answer is a hard no, notebook type programming should stop completely, and you absolutely must switch to a text editor, export your notebooks, clean them up, remove everything, and then turn them into a library. I think that space warrants a richer exploration of the question. The tools are not quite there yet. So there's folks in the Jupyter team that have, for example, written hooks using the Python import hook machinery to allow you to import code from a notebook. Now, a notebook tends to have a lot of top-level code. If you naively say, read all the code and run Python import on it, it's going to be a disaster, because there's going to be a lot of top-level execution. But you can do things like look at it and look at the AST that it generates, the abstract syntax tree that it generates, and say, I'm only actually going to consider library material, class definitions, function definitions, and other necessary things. And that's what I'll pull in, because I will assume that if you defined a few functions in a notebook, that may be the reusable part, that may be part of 5 other workflows. And the other top-level stuff where you're looking at data and making plots, that doesn't need to be rerun every time we import. So you can be smarter about that. You can think. Now, I'm not saying that's the final answer to the problem, but I'm highlighting that to point to the fact that I think this is a question that warrants kind of quite a bit of open-ended thinking. Knuth here at Stanford pushed back since the 70s on ideas like the more traditional literate programming paradigm. I've often referred in deliberate kind of mirror to that, to notebook-style computing as literate computing, not literate programming, because you're often emphasizing, I'm computing on this thing, rather than I'm writing a program. But I do think that there is kind of an analytic continuation, if you will, between one and the other. What exactly that should look like, I'm not completely sure. I think it's a really interesting HCI/tooling question that we should continue exploring. We're kind of coming out of a long path through the woods with the development of Jupyter Lab as a UI system that gives us a lot more flexibility for what kinds of UI, UX machinery put in front of the user. I think we're going to begin seeing kind of exploration of this, and we're happy to talk about it. But I actually would love to hear I don't know if you have any thoughts, because you are a software, you're more on the software engineering, and I do remember one conversation we had in my office the first time we met in Berkeley, where I was showing you we were discussing issues about doc strings in the standard library and interactive usage, and I was kind of running a little bit of IPython and showing NumPy and Matplotlib doc strings, and I remember you said at one point, you said, oh, I see, this is how you guys use this thing. You guys use it, it's a different workflow pattern, and so you might have a different take on this. And I really don't want to monopolize the conversation. So.
I'm very glad for you monopolizing the conversation because I don't actually have much to add. I can sort of sense that the background of the question from, I think you said you work for Google. So I can totally see that some people who work for a large company like that, I used to work there, where everything has to be under source control and there are all sorts of bots that sort of police the source code that's checked in. And then some developers, and especially people who do a lot of data exploration, sort of don't actually like using the source control all that much. They don't like to have to wait for code review. And so they can effectively hide a lot of data in Jupyter Notebooks. And this is like a modern version of a sysadmin in a corner who had an incredibly large Excel spreadsheet that contained the crown jewels of the company that was barely backed up, and certainly no one else had access to it. And I'm sorry, I don't want to make sort of Jupyter look bad or anything. I can just sort of see where the question is coming from, because from the people who manage the software engineering side, it's very annoying that some people are just circumventing the whole code review workflow by using different tools. On the other hand, from the perspective of the researcher who is doing data exploration, the source control adds nothing to their workflow. It just adds friction. And so, yeah, I have not much to add except, yes, this is a conversation we will continue to have. And there are probably times when you want your entire notebook under source control so that you have a sort of log of lab activities. People who work on patents tend to need to keep very meticulous logs, I've been told. But there are also times when the source control gets in the way, or when after several weeks of making lots of silly micro commits, you just want to merge it all into a single commit that says, here's all the new code.
I have a suggestion. Do I need a microphone?
No,
We'll repeat it for you.
I got clear about in the computer age, but anyway, that's explains my gray hair. But as part of that process, we learned to think on the tools of multi-representation. Like for the VLSI editor we did at Yale, you have either the CIF code or layouts. Let's say at least 2 screens, whatever you want to do, but basically multi-representation. That was very useful because some students are better at one versus the other, and you can make clean versions of each side, and yes, then you have to worry about translating link between. I understand it, but it's very doable from a mathematical point of view. If you make that invertible in some sense, that's helpful but hard. Anyway, it's a longer discussion, but I just want to bring it out because I did it at Yale and ETH Zurich, and against the recommendation of so many experts, but from a teaching point of view, it definitely was a success.
Okay, I can't possibly summarize all that, but the suggestion was to consider multi-representation, where you might have 2 different representations of the same data that can be transformed back and forth without loss. And for some people, one representation may be more useful, and for other people, the other representation may be more accessible, and that makes total sense. And maybe Jupyter Notebooks and source control are just 2 sides of the same coin.
So Guido, you talked about why scientists might not want to use source control, but why would software developers want to use Jupyter? Do you use Jupyter for productive stuff? Do you do experiments? Do you use it for data analysis? What do you use it for?
So the question is, why would software developers use Jupyter? My honest answer is that I have barely tried it out. It's like, It's a very different beast. I love watching other people who are good at it do their thing with it. I, in general, don't work with the kind of data that requires that type of visualization. And maybe I'm sort of restricting myself, but usually I'm working on either integration scripts between different systems, or I'm working on something to do with the core language implementation. And I sort of, my existing tools are what makes me fly there. Anything to add?
I guess the one thing, I'm certainly not a software engineer, but I have done a reasonable amount of software development. And the one thing that I did find, and IPython at its heart did have a lot of features, because I also did use it while doing just software development. And the reason, and I think this was part of my, at that conversation in 2009 at Berkeley, my kind of prodding about doc strings in the standard library and whatnot, was because I use IPython in either at a terminal or in its kind of notebook incarnation, precisely as a tool to explore, yes, and often it's scientific data, but if I'm doing software engineering, it's often just a tool to understand a library. So if I am going to write a piece of code, it's a really handy way of saying load a library. The tab completion is superb, and we've made it super powerful and flexible and whatnot. There's ways of querying the namespace in various ways. There's these question mark operators that show you as much as you can about it. It's got all these little things that basically, it's possible that IntelliSense and some of the nice IDEs these days have all of that. Certainly back in, even with a souped-up Emacs in 2002, 2003, 2004, it wasn't quite like that. And so for understanding a piece of software that I was writing, it helped me a lot. And for understanding the ancillary tools that I might need, this and that library and whatnot. So I found it much faster to import, especially in Python, right? Import something, begin tab completing, question marking, digging into it, and writing like 3-line fragments to check it out. And then often just like dumping that to the screen, copy pasting it into a text editor, and then moving on from there. So at that partnership where it wasn't to explore a data problem, but just to explore a software problem, for me was quite useful. And maybe I was just a poor user of Emacs, and that I just happened to use the tool that I knew.
Well, just to follow up, snippet management is one of the problems that every software developer has. You know, these little 3-line mantras that you might want to use and remember. So is that something that Jupyter Notebook is good at managing?
So the question is whether Jupyter Notebooks are good for snippet management. I've never thought of that before, so I have no idea. It's possible someone has written some little extension for it, but I have no idea.
What's the relationship between Jupyter widgets and Jupyter Lab?
What's the relationship between... What's the relationship between Jupyter widgets and what?
Jupyter Lab.
Jupyter Lab. Oh, Jupyter Notebooks and Jupyter Lab. Two completely independent things. Jupyter Lab is a new UI for what we used to call Jupyter Notebook, which when you opened it was actually an application that had notebooks and terminals and text editors and a file manager and extensions. And Jupyter Lab is a new application that has all those same things, but with a proper modular system where they interoperate and they can talk to one another and you can lay them out on the screen. So Jupyter Lab is a new UI for the things that you would have done by running Jupyter Notebook at the command line before. Jupyter Widgets is a completely separate project. It's within the Jupyter world, but it's another sub-project to provide interactive controls in JavaScript, by which I mean buttons, sliders, menus, checkboxes, JavaScript live interactive controls that are connected to the Python core and where actions on the controls automatically modify the state of the Python code. So there's a protocol that connects the two. It's a JavaScript layer, there's a Python layer, and there's a communications layer between those, and APIs in Python to help you say, for example, I want to explore this function makes a figure, and there's a parameter a that I can vary between 1 and 10. And so you can say with one line of code, say call that function interactively and make a vary between 1 and 10 with just one line, and then it will make a widget with a slider that goes between 1 and 10, and as you drag it, it will call the function and plot it. So it's the machinery to give you interactive graphical controls at a very small local level. It's not for building Photoshop. It's not a GUI framework for writing a major application. It's a way of getting small, quick and dirty interactive controls, or not so quick and dirty. The machinery does let you build reasonably sophisticated graphical controls, but typically for sort of exploring a specific question. So they're very useful for education, and they're very useful for kind of scientific exploration.
So my question is for both of you. So what do you envision is the next biggest feature of Jupyter and Python? It can be in the long term. It doesn't have to be in the near future.
That question always comes up, and I am terrible at it. I have all these stories to. Sorry, the question was, what is the next big thing in Python and in Jupyter? So I always struggle with that because I know what 10 years ago what the next big thing was going to be, because by now that has been the most recent disaster or success. But what's next? It always seems to come out of left field. I am bad at predicting the future. I did not see social networks coming at all. And so, I don't know, some people are still trying to get the GIL out of Python, but they still haven't fixed the fundamental problem that a single-threaded program is twice as slow when you remove the GIL. You mean you win it back if you manage to parallelize it at least 4x or so, but for a lot of code, parallelizing is really hard. And so unless you already have a very parallelizable problem, like handling lots of concurrent independent web requests, removing the GIL is not going to buy you much. And we don't want everyone else's code to slow down. So that's probably not it, or maybe it is. Maybe we'll have some way of getting the best of both worlds. It could be some future asynchronous world where like all the network libraries in the standard library actually are fundamentally asynchronous, and the synchronous calls on top of them are just little shims that wait for some event to arrive. That's not where we are today. That's what some people hope to accomplish. I don't know, when will Python 4.0 come out? Is it going to be in 5 years or in 50? You tell me. Come up with the next big thing, and our community will be welcoming you to develop it further. Oh yeah, there are two things that are complete wildcards are web and mobile, of course. At the most recent PyCon, there was a really good keynote by a guy named Russell Keith McGee. Watch that video, is all I can say. So what's the next big thing in Jupyter?
What he said. Well, I'm also, so it's like the fine print in hedge fund things, right? Past performance is not a good predictor of future results. I don't know. We do have a lot of open questions in Jupyter. Which one of those will turn out to be impactful, meaningful? I'm not sure. I'm probably as bad as almost anyone else at predicting that. But I can also say what he said. Watch Russell Keith McGee's talk. I didn't go to PyCon, but the one thing I watched last week, I was giving a lecture at Columbia, and in preparation for that, the one thing I watched was Russell Keith McGee's talk. It is very good.
One of the things that Python has done an exceptional job with is maintaining compatibility backwards and forwards and managing the evolution of the design. What happens in Jupyter now? How is that managed? Is there a process like the PEP process and the decision making that goes on inside of the Python community?
So, yeah, in fact, we have a process which is modeled after the PEP process. It's called the Jupyter Enhancement Proposals, and we have a more complex governance issue, I think, in the sense that on paper it is modeled very closely after Python. We have a structure called a steering council. I am nominally the BDFL, and this was modeled directly after that. However, we are evolving that, and we are evolving that because the project precisely has such a complex scope, and I think Python has managed to do a kind of a good job of separating kind of what the core team worries about versus what the kind of rest of the community worries on, and other projects. In Jupyter, a lot of what happens in Jupyter is kind of within our scope, and so we're sort of figuring out what are good governance models to evolve towards for better managing that. But to first approximation, yes, we have similar ways of discussing enhancements, and we do pay painfully close attention to backwards compatibility. At this point, we track the growth of notebooks on GitHub, for example, just as a course metric of adoption. There's now millions of them. They continue growing. We know that people have invested enough of their work in building these things that we're not simply going to nilly-willy make changes, which is hard. It's a lot easier to design software with no users, in a sense, because you can do whatever you want, right? We now have a huge responsibility, and so we can't break anything. The format on disk of notebooks has changed very little since the very first one, and those changes, they were minor, and the tool knows how to move back and forth between them. And even though we know today there's issues like, well, version control of a JSON data structure is kind of a pain in the ass, we don't lightly take kind of the notion of breaking that and coming up with a new one, because we know the impact would be huge. So we think very slowly about those questions.
You want to go first? Go ahead. So, question on the notebooks. What about the confused state problem, in the sense that between the different cells? What are your thoughts on that?
The question is, what about the confused state, and which means, what about the disconnect between the linear structure of a document, which you can read top to bottom, and the fact that as you've been executing cells, the real state of the system may be completely different from that. That's a fundamental problem, not of Jupyter, but basically of any notebook type system. It was present in Maple and Mathematica 25 years ago. I think that's another interesting HCI problem. I think fundamentally, if you have, and there's good reasons to want a linear document, if that document is attached to a computationally stateful entity, there's the potential for that mismatch to exist. So the question is, how do you surface it better, which I don't think we're doing a good job, and I think there's good UI ideas that you could come up with, ways of showing dirty state, changing colors, indicating to the user which parts, where the execution flow has happened. I think there's a lot of good UI, UX that could be put into that. And second, what are the scenarios where you might actually be able to afford stronger constraints where that doesn't happen? You can prevent that from happening if you pay the price. If you pay the price of always forcing recomputation, if you pay the price, a spreadsheet doesn't have that problem because a spreadsheet recomputes everything on every change. Well, that's not realistic in all of Jupyter workloads, because there are many workloads where like a cell takes 5 minutes to compute. You can't think that that cell is going to be recomputed every time you change a letter down the road. But there may be scenarios where recomputation is viable, and the pedagogical value of not exposing that complexity warrants paying the price of recomputation, because maybe they're smaller problems, small little educational things. So again, I think it's a good HCI research and UX question, where I don't think we have the final answer. The problem isn't going to go away. This is the first one that comes up on every usability discussion about these systems. It's not unique to Jupyter. It's fundamental to the platform. The question is, what are good creative ideas to tackle it?
Yeah. This is really a question to both of you, since both of you basically created a community from nothing. It's a social question. So I see a gap in the universe. I think I know how to fill it. It's building a language for building DSLs so that knowledge workers are working in a great environment. Anyway, not to talk about the thoughts on that, but the question is, you both built a community where you yourselves built enough code that it was useful to the first people who used it. I'm not sure my idea fits that model. That is, I feel like if I had 5 or 6 guys, especially a few that really know compiler design, would be able to build the system that bootstraps. My question is how to build the community in the very early stages. And I'm also kind of just curious about those very early stages. The only thing both of you said was, oh, I put it out there and boom, everybody showed up. I'm not so sure that would work for all ideas.
Oh, how to summarize, how to build a community in the very early stages, especially if you have an idea, I think, that requires a lot of code to be written to start with. Well, some ideas, you may find it easier to get VC funding and do it in the form of a startup than do it as an open source project. I mean, I'm not sure I can imagine an open source project that requires the effort of 5 engineers for a year. I don't know if that's the sort of the approximate scale you were mentioning, but something that requires that much effort before it's ready to be shared is probably not a great thing to start open source at that point. You sort of you got to think smaller. I put like 3 months in it before I shared, and
It's valuable at 3 months.
yeah, it was useful at 3 months. And it was not done at 3 months, but it was useful. And so, I don't know, I sometimes read interesting books about evolution. And it's amazing how very complicated biological systems could ever have evolved little steps at a time, and yet we know that they must have evolved that way. There are many, many intermediate forms that do not look as complex as a brain or a heart or even a dinosaur that can sort of be made with less effort than 5 engineers for a year. That like 1 engineer for 3 months can put a dent in some problem and open source it at that point. Or you can sort of try to attach yourself to an existing community, not necessarily take over, but sort of get people excited about an idea. And I think Fernando probably has some good things to say as well.
Actually, precious little beyond that, to be honest, because I think that there actually are ways to get funding if it looks researchy enough. DOE, NSF are starting to fund.
Well, it's more getting people excited about it, I think.
But actually the problem with those things is precisely that they will fund you to have 10 people working for 3 years before there's something useful, and that's the wrong thing to do. I fully agree with Guido. That early push of mine in IPython when I disappeared was 6 weeks. 6 weeks plus the implicit contribution of 2 other people, whatever time they had put into some of their stuff. But they were both small. I mean, all things considered, they were small things, small amounts of code. And that was true. It was useful. Like that thing, that IPython 0.1 on comp-length Python in December was useful. It was missing a ton of stuff, but it did something. And the value of that is that you get immediate real world driven, that evolutionary, I mean, evolution is driven by feedback loops. Evolution is driven by selection pressure. And you get that selection pressure early on. Design in a vacuum is design without selection pressure, and you end up with 3 heads and 4 elbows, right? And so I strongly, strongly encourage anyone to really put out something that can do something useful early on, even if the full problem seems to be huge. Find the piece you can bite off early and quickly and in a lightweight manner, and what the right feedback path is going to be for that.
Before we get to the next question.
We're running out of time.
Okay.
We have 2 more people.
Oh, I just had one thing to add, which is that if you spend a bunch of time developing something and then you launch it, expect that your life after the launch is going to be nothing like what you planned for. The sort of the feature request, what the users are going to want, what they're going to do with it is going to be unexpected. And that's a good thing, but it means that you must plan for life after the launch to be very chaotic and sort of unplanned. And now you said there were 2 more questions?
We have one there and one there.
So, full disclosure, I don't use notebooks day to day, but I support the students and the faculty who do. And one of the issues on the subject of like submit a notebook as your paper submission is I'm finding the problem becomes, and it's more than just notebooks in general, it's not just the notebook, it's the entire environment in which the notebook runs.
Yeah.
How do you package that? Like, you might say, oh, here's the notebook, and here's a requirements.txt file. But if you look at numeric, for example, you cannot hit install numeric anymore. It can't find it. So those go away eventually. And you can't submit a container because, especially in languages like R, they will very carefully, specifically target the CPU you are building on, which is not the CPU you're running on in the future. So this is a problem that's more than just notebooks. But the reason I bring it up here is because the notebook kind of buries the problem just a little more, which makes it harder for the future. So what do you do to deal with that?
So the question is about basically reproducibility, and I do think that it's a complicated and nasty enough problem, and you've highlighted issues all the way down to CPU architecture issues, that there's no known single answer to it. I do think that the combination of basically what we're doing with Binder, which is the project that tries to kind of capture that famous quote of Donna Hobach and Claire about getting the whole environment, or not just the notebook, but the whole environment, and facilitating and automating the process of creating that as much as possible, is part of the answer. Yes, it is a container. Yes, it means that container is going to have some of these issues, but there are ways of, for example, having the reasonably generic x86 versions of the linkage done so that at least it runs, and it runs in the cloud. And I think it's one of those problems where you have to have a defense in depth kind of approach of saying, okay, well, that entity, that binder is a container, but it also actually has PDF and HTML versions of the document. It has the code, it has the libraries, so that you can do human levels of validation as well. So if some of the layers fail, if the microarchitecture has changed, if it turns out you needed a weirdo GPU that doesn't exist in 20 years, there's other levels of human validation that you can still do. Because there is no magic perfect, we're going to kind of teleport the world 100 years into the future, and every line of code we have is going to run. I don't have a magical answer to that one. I do have kind of a layered approach to the problem.
Is Jupyter widget the vision to be like shiny? If not, what is?
So the question is the relationship between Jupyter Widgets and Shiny. Jupyter Widgets as a core project is just a library, right? Shiny kind of has also a deployment model and a specific website and a business model around it. The Jupyter Widgets is the part which is the library, and it's not, I think today Shiny, and I'm not an expert in R, so maybe I'm butchering this. I think originally some of that was very specifically tied to visualization. Jupyter Widgets is a completely generic architecture around interactive controls connected on the client over a network protocol to stateful kernels, and in fact they can be implemented in non-Python languages. So now Jupyter Widgets has there's a C++ backend. Julia has a backend, so you can. The architecture is more generic. You can expose that as a standalone web view, sure. There's a project actually out of the QuantStack folks who do the C++ kernels called Voila that makes it very easy to kind of expose something like that. We don't have a business model of running it like Shiny. That's a very specific hosting question. The architecture between Jupyter widgets and things like Voila provides all the pieces for that. Someone could do the hosting. Feel free to do it.
Okay, we're running out of time, so. We're effectively out of time. I've lost my. There we go. In any case, thank you for coming. There's lectures scheduled for every Wednesday on through the rest of the year. Some of them will be fascinating, some perhaps less so, but it depends upon your taste. In any case, it was very pleasant having you all here. I think we learned a bit. I'm pleased that the notebooks are finding a home, and I'm going to write my next paper that way. I think it'll be an extremely interesting experience. Thank you very much.